Welcome to the video lecture series on digital image processing. Till our last class, we have talked about various image processing techniques, and for last few lectures, we were talking about image segmentation techniques. And as we have seen that image segmentation is nothing but a process of partitioning a given image into a number of sub images or into a number of sub partitions. And we have talked about various techniques for partitioning the image into a number of partitions or into a number of components. So we have seen that image segmentation techniques can basically be divided into two different categories. One of the category is discontinuity based image segmentation techniques, and the other category is similarity based image segmentation techniques. In discontinuity based techniques, what we look for is some abrupt changes in the image gray levels, or if it is a color image, some abrupt changes in the color information in the images. And based on this abrupt changes in the intensity values in the images, we partition the images into different components. So, essentially in discontinuity based image segmentation technique, what we look for is some isolated points, or we look for some lines, or we look for some edges and similar such discontinuities present in the image. And based on this discontinuity, once we detect some such isolated points or say points lying on a line obviously is a boundary between a lighter image region to a darker image region. And once we identify those points, then by some post processing technique, we try to link those points, and after that we get partitioning of the image into different regions, and naturally in this case the partitioning is based on the discontinuity approach. In the other case, in similarity based technique, we have seen different type of techniques. The first one that we have seen is the thresholding, and we have said that it is one of the simplest approach for segmentation of an image. So, in thresholding based approach, what we have done is, by some means we try to find out a threshold, and thresholding an image means all the intensity values, the regions with the intensity values which are less than the threshold is put to some partition, some segment, and the image regions where the intensity values are greater than the threshold, they are put to some other region. So, when I put these image pixels to different regions based on their intensity values compared to the threshold, what we essentially do is we partition the image into a number of regions where the intensity values in different regions are different, and intensity values in certain regions are similar in the sense that either they are greater than the threshold for a particular region, or the intensity values of all the pixels in another region is less than the threshold. The other kind of segmentation technique based on the similarity measure we have done is the region growing operation. So, in region growing, what we have done is, again by some means we try to identify some seed points, and then we try to grow the region from the seed points based on some similarity measure. So, when you grow the region, you ascertain that a point will be included into a particular region if the intensity is similar to that region, and at the same time the point is also connected to that particular region. So, you start from a number of seed points, and from each seed point you try to grow the region based on similarity of intensity value as well as the connectivity property, and that is how we get an image segmentation based on region growing technique. And the last approach under this category, that is similarity based approach, that we have seen is region splitting and merging operation. So, here you start with the entire image, then if the image intensities, if the pixel intensities over the image is not similar, then you partition the image into 4 different partition, or you make 4 different quadrants, and then you check for the similarity in each of the quadrants. If in any of the quadrant you find that all the pixels have similar intensity values, you do not partition it anymore. But a particular quadrant where if the image pixel intensities are not similar, you partition again, you subpartition it again in 4 different quadrants. And this process of splitting continues until and unless we find that a quadrant size is less than a given size, or the intensities in each of the quadrants, image intensities, pixel intensities in each of the quadrants are similar. Now, while doing so, it is possible that a connected region of similar intensity will be divided into a number of different partitions. So, in the second phase, that is the first phase which we have done is the splitting, that is a image is split into a number of quadrants, and this process continues until and unless we find that image intensities in every quadrant is similar, or the quadrant size reaches a minimum specified size. So, after splitting operation, as a connected region may be split into a number of subregions, so we go for the second phase, which is the merging operation. So, in the merging phase, what we do is we take the neighboring regions which might have been split into 2 different regions, but their intensity values are similar. So, in merging phase, you try to merge them in a bottom up fashion, and once your splitting and merging these 2 phases are complete, you get partitions of the image or segmentation of the image into different segments, where the intensity values in different segments will be similar, in each segment will be similar, and the intensity values will be in the different segments will not be similar. So, these are the different segmentation techniques that we have talked about during our last few lectures. Today, what we are going to talk about is something different. That is, we are going to talk about a topic called mathematical morphology, and we will see its application in image processing. So, in today's lecture, we will see what is mathematical morphology, and we will talk about different morphological image processing techniques, and in particular in today's lecture we will try to cover the topics of dilation, erosion, opening and closing operations. We will come to each of these techniques, discuss each of these techniques one by one, and then we will see that what are the applications of these techniques in our image processing operations. So, firstly let us see that what is morphology. Now, morphology is a term which is widely used in the field of biology, and it tells you that it discusses about the shape and structure of different animals, different plants and so on. In our application, we will talk about morphology to discuss about the image processing techniques which take into consideration the structure and shape of objects. So, the image processing techniques based on the structure and shape of the objects are classified as morphological operations, or this is nothing but the application of mathematical morphology in image processing. Now, when we talk about such morphological operations, this has a number of applications. For example, in one of our earlier lectures, we had shown this example, where we have an image of an object. Then what we do is, we try to separate the object region from the background region, and for separation of the object region from the background region, we have applied a simple threshold operation, and by applying the threshold, the kind of image that we get is shown on the top right corner. And here you find that all the white pixels which are supposed to belong to the object region within this white region we have a number of black dots. Now, these black dots we consider them to be noise. This noise can be filtered by the morphological operations, and after doing the morphological operations, the filtered image that we get is shown on the bottom. And we will see through our discussion today and our subsequent few lectures that how such filtering operation can be done by using the mathematical morphological techniques. So, these are various applications, one simple application that I have shown earlier. The other applications of this mathematical morphology is in pre-processing of images, that is in case of filtering. The example that I have just shown is nothing but a filtering operation, because here what we have done is all the black patches which are present in the segmented image, if I consider that those black patches arise because of the presence of noise, then by morphological operation we are eliminating those effects of those noise by using the morphological filters. So, it is a pre-processing kind of application where the application is to filter the noise present in the image. The other application of the image processing techniques can be for shape simplification. We can have a situation that we have an object of very complicated structure, but it is possible to break that complicated structure into a number of substructures, where each of the substructure will be simple in nature, so that it is easy to describe or easy to quantify the shape attributes of that particular structure. So, in such cases these morphological operations will also help us to simplify the shape of a complicated structure. So, naturally in this case the complicated structure will be broken into a number of substructures, where each of the substructures are very simple in nature, so that we can describe them very easily. Then, as we said, that morphology is a topic which deals with the shape or structure of the objects. So, we can use the object shape for segmentation operation as well. So, the segmentation using the object shape is another major application of these morphological techniques. Morphological techniques can also be used for image quantification. By quantification, what I mean is we can find out the area of the object region, we can find out the perimeter of the object region, we can find out the boundary of the object region, and many such related attributes of the object regions. And this is what I mean by object quantification, and later on we will see that the morphological operations or morphological transformations help us to a great extent for quantification of objects. Morphological operations can also be used in other applications in other cases, for example, enhancing the object structure. By enhancing, what we mean is, in one of our earlier lectures we have seen that given a shape, a two-dimensional shape, in many cases the two-dimensional shapes can be better described by using the skeleton, and one of the skeletons we have seen is the medial axis. So, these morphological operations are also very useful to find out the skeleton of an object. Similarly, these are also useful for thinning operation, these are also useful for thickening operation, these are also useful to find out the convex hull of a set of points. We will come later what is meant by convex hull. These are also useful for object marking, and there are various such applications of the morphological operations. Naturally, it is not possible to cover entire morphological operations in this particular course, and that is beyond the scope of this course, but we will look at some basic image processing operations which employs morphological techniques. So, as we said earlier that by morphology what we mean is it commonly denotes a branch of biology. We said that morphology is very a common term in the biology, and it deals with the form and structure of animals and plants, whereas in our case when we mean use of mathematical morphology in image processing, sometimes it is also called image morphology. By this we mean the mathematical tool which helps us to extract image components which are useful for representation, description of region shape, boundary, skeleton, convex hull, etc. Now, whenever we go for such mathematical morphology in image processing or image morphology, the basic assumption is an image can be represented by a point set. That is, we can, given an image, we can represent an image by a set of points. What do we mean by that? Let us look at this particular figure. So, as you find that we can say that this is nothing but a binary image, where the shaded regions represents object pixels and the black regions represents the background pixels. So, this is nothing but a binary image. So, when we talk about this mathematical morphology, initially we will consider initially we shall concentrate on application of mathematical morphology to binary images, which we also called binary morphology. Later on, towards the end of this topic, we will see that how this binary morphology can also be extended to take care of gray level images, and we will call that as gray level morphology. So, as I was saying that the basic assumption in application of mathematical morphology in image processing is that the images should be represented by point sets, or I should be able to represent an image by a set of points. So, looking at this example, where I have shown a binary image, and as I said, this shaded regions represents the object pixels and the black region represents the background pixels. And here you find that this particular binary image can be represented by a set of point. So, I can write a set X which is nothing but a set of points, the points belonging to the object region. So, in this particular case, if I say that this is my x direction and this is my y direction, you find that the coordinate of this point is nothing but 2, 0. So, this point 2, 0 is a member of this set X. Similarly, the point 2, 1 is also a member of this set X. The point 1, 2 is also a member of this set X, but point 2, 2 is not a member, because this pixel is a black pixel and it belongs to the background, whereas the point 3, 2 it is a member of this set, which is this point. So, likewise, I can consider the other points which belong to the object region to be member of this particular set X. So, you find that this object is now represented by a set of points, where a member of this set represents the corresponding point is an object point. Similarly, the background pixels in this particular image can be represented by X complement, because all the points which does not belong to this set, this point set X, they belong to the complement of set X or X complement. So, the background pixels is also nothing but a point set which is complement of the set X, where set X is a point set representing the object pixels. So, this is what I mean by an image should be represented by a point set. And once an image is represented by a point set, then all the morphological operations on the images are nothing but some set operations on those point sets. So, because these morphological operations will be set operations, let us quickly review some basic set operation techniques. So, as we all know that suppose I consider a set in a two dimensional space. So, I consider a set A, point set A in say two dimensional space Z2, and if a point say A, because we are considering two dimensional space. So, a point in this two dimensional space will be represented by an ordered pair. So, this point A, if I represent it by an ordered pair say A1, A2, then our first definition is, if this point A is a member of this point set capital A, then we will write as A belongs to capital A. So, this is what says that A belongs to the point set capital A. Similarly, given another point in this two dimensional space say B, if B does not belong to the point set A, we write it as B does not belong to the point set A. So, these are some basic set operations or set notations. Then we can also define a subset operation, that is, we say that a set A is a subset of set B, where both the point sets capital A and capital B are in the two dimensional space Z square. So, we define the point set capital A is a subset of the point set capital B if every element in set A also belong to the set capital B. However, the reverse may not be true. If I have an element in set B that may or may not belong to set capital A, but every element belonging to set capital A must be a member of set capital B. In that case, the point set capital A is a subset of the point set capital B. We also have set union operation. So, for two sets capital A and capital B, the union operation A union B is the set of elements taken from set A and set B. So, if I combine all the elements of set capital A and all the elements of set capital B and take them together, then the set that I get is the union of the two sets capital A and capital B. We can also have set intersection operations. So, by intersection, the intersection of two sets capital A and capital B means that all the elements in A and B which are common, that is, if an element belongs to set A and that also belongs to set B, then that particular common element will be a member of A intersection B. So, A intersection B really represents the common elements which are common in both set A and set B. Similarly, we can have set complementation. So, by complementation what we mean is a set or complement of a set capital A, this is nothing but all the elements B such that B does not belong to set capital A. So, set of all the elements which are not members of the set A forms the set A complement. And we have seen in our last example that if I represent all the object pixels by a set say capital X, then all the background pixels will be represented by x complement, because the background pixels are not object pixels and the vice versa, the object pixels are not background pixels. We can also have set difference operations, that is, we define set difference A minus B, and which is nothing but it is the set of all elements say W such that W belongs to A and this W does not belong to B. So, essentially if we have some common elements in the sets A and B, so if I remove the common elements from set A, then whatever set I get, that is the set of elements which are in the set difference A minus B. Similarly, we can have other set operation like set reflection. So, what is this reflection? So, reflection of a set say B, reflection of set B. So, this is usually represented as B hat, and B hat is nothing but say it is the set of W such that W is equal to minus B for B belonging to set capital B. So, if I have a set of points which I call as capital B, then all the points belonging to set B, if I negate them, then all those negated points, set of all those negated points is actually the reflection of set B, and this reflection of set B is represented by B hat. Similarly, we can have a translation operation on a set. So, if we translate by a vector say z, which is equal to z1, z2, components of this vector z are z1, z2, then the translation of a set A by vector z, which is represented by A with subscript z, is given by, it is the set of all points C such that C is equal to A plus Z for A belonging to set capital A. So, if I shift all the points belonging to set A by this vector capital Z, then the set of all those points, all those shifted points form the set A Z or the set A which is translated by vector Z. Now, as we are considering the point sets, and we know that in a two dimensional space a point can also be represented by a vector. So, a point set we can also say that it is a set of two dimensional vectors, and as we have said that all our morphological operations will be based on set operations, and some of the set operations which are usually used in morphological transformation that we have just briefly described. Now, let us see that what we mean by a morphological transformation. So, we say a morphological transformation say psi. So, this morphological transformation psi gives a relation of the image x, capital X, and as we have just said that this image capital X is nothing but a point set or set of points. So, this morphological transformation gives a relation of the image x with another small point set or another small image say capital B, which is called a structuring element. So, in this case what we have? We have an image say x capital X and we have a small structuring element or a small image capital B. So, this morphological transformation actually describes or gives a relation between this image X and the small point set capital B, which we are calling as a structuring element. Now, the way we compute this relation is similar to the way we have done the convolution operation or the way we have done the image registration operation. So, in case of convolution operation, what we have done is we are given a big image and we are given a small image. So, there what we do is you take this small image and move this small image systematically over the big image, and for each such shift or each such translation of the small image over the bigger image, you do some computation which is nothing but the convolution operation. So, here also for morphological transformation or for morphological operation, what we will do is we will translate or we will move the structuring element systematically over the given image X, and for each translation of the structuring element in the given image, we will perform some operations which the type of operation will depend upon what type of transformation or morphological transformation that we want to do. So, firstly we will talk about some simple morphological transformations, and one of them we call as dilation. So, what is dilation? There are two different definitions of the morphological dilation operation. However, we will see that both these definitions lead to the same result, or in the other sense that two different definitions are identical. So, what are those definitions? So, first what we consider is the dilation operation. And this dilation operation is denoted by a symbol you have a cross within a circle. So, this is the symbol which is used to represent dilation operation. And this dilation operation is actually implemented, is defined in terms of set addition or vector addition. So, if I have an image or a point set X and I have a structuring element say capital B, then as we said that all morphological operations actually define a relation of the given set X with the structuring element B. So, this dilation operation has to be implemented or has to be defined with respect to the structuring element capital B over the image capital X, which is nothing but a point set. So, we represent X dilation B like this, and this X dilation B is defined as it is the set of points P obviously in the two dimensional space. So, the two dimensional space we have written as z square such that P is equal to X plus B, where X belongs to capital X and B belongs to capital B. So, this is our first definition of the dilation operation. So, what it says that I have been given two sets, 2 point sets. The first one is capital X, which represents an image, and the second one is capital B, which represents our structuring element. Now, each of these sets are nothing but, as we have said, that set of points or set of vectors in two dimensional space. So, our first definition of dilation operation says that I take every element from set X, capital X, and every other element and every element from the set capital B and add them vector wise. So, you take vector addition of every element from set capital X with every element from the set capital B of the structuring element and set of these resultant vectors that you get, that gives you the dilation X dilated with the structuring element B. The other alternate definition of the same operation is given like this. We can also define X dilation with B, the structuring element B, in such a way that again it is the set of points P such that if I take the reflection of B and translate this B with vector P, then take the intersection of this with set X, this should not be equal to null. So, I have this structuring element and we have defined what we mean by the reflection of a set. So, I take the reflection of the structuring element capital B and then translate it by a vector say P. Then this I take the intersection of this translated reflection of set B with the set of points capital X. And if this intersection is not null, in that case the translation vector P is a member of X dilation with capital P. And we will see that though we have two different definitions of dilation, but both these definitions are equivalent in the sense that they produce identical results. Now, first let us see that what we mean by this dilation operation. So, let us take an image say like this. Say I have a binary image which are represented by say these points. So, these are the points which belong to the binary image. So, this is my set of points capital X and I define a structuring element say capital B, where this structuring element contains say only these 2 points. Okay. And obviously, I have to have some coordinate system for both my image as well as the structuring element. So, I assume say this is the origin of my point set capital X and suppose this is the origin of the structuring element B. So, considering these two origins, now you find that this point set X is nothing but a set of points where this X can be represented by this point set consisting of points say 3, 2, points 2, 2, points 3, 1. So, similarly, I can consider the other points in it. So, I get the image capital X as a set of points or a set of vectors. Similarly, this structuring element is also nothing but a point set where you find that this point set is nothing but the points 0, 0 and it includes the point 1, 0. So, as we have seen the definition of dilation operation, that is I take every point from set X and I take every point from set B and you do the vector addition. Take a point from set X, take a point from set B, do the vector addition of these 2 points and this vector addition, the resultant vector is a member of X dilation B. So, by doing this, when I add all these points in set say X with the first vector or the first point in our structuring element capital B, which is nothing but 0, 0. So, these points will be written because every vector from set X when it is added with 0 0, the resultant vector remains the same. So, all the points in set X are also members of set X dilation A. Similarly, if I take a point from this set X, say 3 2, and add to this a vector from our structuring element B, which is the 1 0, this is nothing but 4 2. So, this point 4 2, which is over here, this is also a member of A dilation with B. Similarly, when I take this point 2 2, add to this the vector 1 0, what I get is 3 2. Now, 3 2 is already member of X. Okay. So, this point remains a member of X dilation with B. If I consider this point say 3 3, this point, okay, add to this vector 1 0, then my resultant vector becomes 4 3. So, this is my resultant vector, which is also a member of this A dilation with B. So, if I continue like this, you find that all the points which were belonging to set capital X, they remain in capital X dilation with B. In addition to that, I get other additional points because of addition with this vector 1 0. So, these additional points are nothing but these points. So, these are the points which will be added to X dilation with B. So, our X dilation B will be set of all these points. So, this gives us what is A dilation with B. Now, let us see whether we get identical result, the same result, if I apply two different definitions. So, for that I consider a similar kind of situation, and for clear explanation, let us take a very simple situation. Again, as before, I consider say this is the origin of the point set X. So, I am having two different instances. So, this is my point set X, this is also point set X. Okay. And I consider say this is the origin of our point set B. So, this is the origin of our point set B. Okay. And I take a single point in our image. So, this X contains this single point, and what I do is I take the structuring element consisting of only 2 points like this. So, you find that this X contains only the point 3 2 and the structuring element contains 2 points, one is minus 1 0 and other one is 2 0. So, these are the 2 points which belong to the structuring element. So, you find that these 2 points are because I have taken the origin at this location, and over here what I consider is the reflection of B. So, in this case the reflection of B will be this particular set. So, the reflection of B will be nothing but minus 2 0 and 1 0. And this set X is again because it is 3 2. So, this is the only point which belongs to set X. So, in the first case, if I apply our first definition, that is dilation as a result of vector addition. So, what I have to do is I have to take the point from the point set X and add to it every vector from point set capital B. So, by doing that, what I will get in this particular case is my dilated image will consist of only these green boxes. So, these are the only 2 points, because if I add minus 1 0 to this particular point, I come to this green box, and if I add 2 0 to this point, I come to this green box. So, these are the 2 points which will be members of X dilation B following our first definition. Now, what will happen if I apply the second definition? The second definition is in terms of translation of the reflection of set capital B, and we have said that for all those translations where the reflection of capital B or the translated reflection of capital B intersection with X does not become null, those translations are members of X dilation B. So, if I do that, in that case you find that given this reflection of capital B, if I translate this to this particular location, in that case this point of B translation will be intersecting with this point in our set capital X. Similarly, if I translate this B reflection to this particular location, then this particular point in B translation will be intersecting with this point in our set X. So, here again you find that these are the 2 points or 2 translation vectors which will be members of X dilation with B. So, now if you compare this result with this result, you find that we have got identical results in both of these 2 cases. So, whichever definition we will follow, both the definitions are equivalent definitions in the sense that they give us identical results when we talk about dilation of a given set X with respect to a given structuring element, say capital B. Now, what will be the application of this dilation operation? Let us take again a particular image like this. Say I have an image which consists of say these points. Now, in between I have say a noisy point, so something like this. So, these are my object points, and I consider that these black pixels, these 3 black pixels that I have within this object region, these black pixels are because of the noise. And suppose I consider a structuring element. So, this is my set X, and I consider a structuring element say capital B, which is something like this. So, all these elements are members of structuring element capital B, and when I have this structuring element, the origin of the structuring element I can consider to be this particular point. So, this is the origin of the structuring element. Now, find that if I dilate, if I go for dilation of this given image with the given structuring element, then the dilation result will be, I mean whichever definition you follow, that whether it is vector addition definition or the translated version or the translation of the reflection of B to various locations in our given image X, as we seen that we get identical relations, identical outputs. So, if I go for dilation of this image X with our structural element capital B, then you will find that all these points will be in our dilated output. So, all these points will be in the dilated output, and these noisy points that we had within the object region, they will also be filled up. So, a natural application of this dilation operation, as we have seen in one of the applications for segmentation by thresholding operation, that we had a number of black spots within the object region which are supposed to be white. So, for filling those black spots, we can make use of this dilation operation, as we have seen here that all these black pixels, that these 3 black pixels in the object region can be filled up by dilation with respect to a structuring element like this. So, this output is X dilation with B. Now, naturally in this particular case, we have a side effect. The side effect is, it is good that all these internal noisy points, they are being filled up by white pixels or object pixels, but at the same time you find that our original boundary, the original object region boundary was this. This was the object boundary. Now, because of this dilation operation, the boundary gets expanded. So, in addition to this, all these points are also included in the object region. So, in effect, what we have is the object boundary is expanded. So, this is naturally a side effect of this dilation operation, and we have other operations by which this expansion, the boundary expansion, can be compensated. So, let us now talk about some other operation, which is another morphological operation, that is image erosion operation. So, as we have seen that in case of dilation, what we have is, we have a given image X and we have a given structuring element, say capital B, and what we are doing is, we are dilating this given image X with respect to the given structuring element B, and this dilation operation is defined in terms of vector addition. In the same manner, we can have an erosion operation, where erosion can be defined in terms of vector subtraction. So, as we have seen, in case of dilation, we can have 2 alternate definitions, though the definitions are equivalent. Similarly, in case of erosion, we can also have 2 different definitions, and the definitions are equivalent. So, the definition of the erosion operation can be something like this. So, again here we will have a set X and a structuring element B, because for all the morphological operations, it has to be defined with respect to a structuring element. So, we have a point set X, capital X, representing our image, and we have a point set capital B representing the structuring element. And the erosion of the point set X with the structuring element capital B, this can be defined as per our first definition, it is the set of points, say P, belonging to our 2-dimensional space, say Z square, where P plus B belongs to X for every B belonging to the structuring element capital B. So, this is our first definition of the erosion operation. The second definition of erosion operation can be that the same operation, say X minus B, X erosion with B, this can be defined as the set P such that I take the structuring element B, translate this structuring element by vector P, this must be a subset of our set X. So, you find that this second definition, it says that you take the structuring element, then translate the structuring element by a vector, say P. And if this translated structuring element is a subset of this set X, then the corresponding vector P of the corresponding point P will be a member of X eroded with capital B. Okay. So, or in other words, for all those translations of the structuring element capital B, if the structuring element is contained fully within the set of points X, then the corresponding translation or the corresponding point will be a member of X eroded with B. So, we will stop our discussion here today. We will consider this erosion operation further, and in our subsequent lecture, in our next lecture, we will see some of the properties of the dilation and erosion operation. Thank you.